Hello, my name is Erik Offerman and I work as an associate professor at the Department of Material Science and Engineering of the faculty 3ME of the Delft University of Technology. This lecture is about material selection. In this lecture I will explain you how the Ashby method for material selection works. And this is, in this lecture, focused on materials for which the electrical properties are important. The aim of this lecture is fourfold. Firstly, we are going to look into the material selection method that was developed by Professor Ashby, Emeritus Professor from Cambridge University. Secondly, we will apply this method to electrical properties of materials. Thirdly, we'll derive a material index, or also called a performance index, for the material selection. And fourth, we apply the material index to an Ashby graph for the material selection. The structure of the lecture is as follows. First, I will give you an introduction to the material selection method that was developed by Professor Ashby. Secondly, I will recap some of the basic electrical properties that we will need later on. Thirdly, we will see how to derive a material index and apply that to a case where the electrical conductivity of materials is of importance. Fourthly, we will derive a material index in case dielectric properties are relevant for the material selection. And lastly, we will discuss some exercises. Okay, let's start with the introduction. So this method is based on the method developed by Professor Ashby, and this presentation is based very much on the book that he has written with his colleagues, Materials, Engineering, Science, Processing and Design. So if you would like to read more about it, I refer you to this book. Let's start with the family tree. The materials world, or the material kingdom, is subdivided in several families of materials, namely the following 6: ceramics, glasses, metals, polymers, elastomers and hybrids. So if you look into the family of metals, you can subdivide the metals into several classes. For example, steels, copper alloys, aluminum alloys, titanium alloys, nickel, zinc alloys, and so on. Now, a particular class of materials, like for example the aluminum alloys, can be subdivided in subclasses, and then we're talking about the 1000 series of aluminum alloys, the 2, 3, 4, 5, 6, 7 or 8000 series of aluminum alloys. Now within a subclass, for example the subclass of the 6000 series of alloys of aluminum, we can find different members. For example the 6061 alloy of aluminum. And the accompanying software package says EduPack contains a lot of information about the properties of all these alloys, or all these materials. So if you click on an aluminum 6061 alloy, you will find all of its mechanical properties and a lot of sustainability properties. So that's a very handy database. Let's have a look at an example of an Ashby diagram. The Sage EduPack software allows you to plot graphs like these. This is a graph that shows you the dielectric constant and the dielectric strength of materials. So this is, for example, of interest when you want to select a material for a capacitor. And typically you want to store as much energy as possible in a capacitor and keep the volume of the capacitor as small as possible. And that's good for miniaturization. Now the SES EduPack software allows you to show all the materials that have the required properties. For example, if you're looking for a material with a high dielectric constant and at the same time a relatively high dielectric strength, well, you end up at barium titanate. So from your design requirements you usually know what properties you require, and with the help of the SES EduPack software you can find the materials that fulfill these requirements. Now what you also see in this graph are a number of lines with a slope of -2, and please note that these are logarithmic scales that you see here. All the SB graphs are typically plotted on a double logarithmic scale, and the lines that you see here, they in this case represent lines with a certain energy density. So in this case here the energy density is 1 kilojoule per cubic meter, and as you move on in this direction you see here, for example, materials that have an energy density of 1000 kilojoule per cubic meter. So all the materials that lie on this line have the same energy density. So this is very convenient. Again, coming back to the capacitors, if you want to select materials with a high energy density, you typically want to look for materials that lie in this range, because here you see that these lines of energy density, they become larger when you move more to the upper right corner. Now let's have a look at the material selection process in more general terms. So we start with the design requirements, or in Dutch, the ontwerpeisen. So from the design requirements we derive a required property profile and a required shape of the product or the material. Now from the required property profile we can derive which materials fulfill the requirements set in terms of properties. From the required shape we can derive a process or multiple processes that you can use to actually make the product or the material into the required shape. Now at the same time you see all these arrows, meaning that there are a lot of interactions. So it's nice if you found a process that can give you the required shape for the product, but if the material does not match with it, it still doesn't work. So you have these interaction between material and processes, and material and required shape. And in that sense, the whole material selection process is rather complicated and an iterative process. But suppose now that we found a material that fulfills all the required properties, and we found a process that can give us the required shape, and indeed the process and the material, they also match. Well, that gives us then a cost for the production of the material via that process. And it also gives us what the eco-impact is of producing the product by that material and that process. And we may not be happy with the eco-impact that is derived from our first analysis, so we could maybe reiterate and do the whole exercise once more and find a material and process combination that leads to a lower impact for the environment. It may change the cost as well, so we might, the cost is then too high, have to do the iteration once more and continue iterating until we are satisfied with the combination of the cost and the eco-impact of our material and process choice. Now that leads us to the final choice for our material and for our process. However, you should also have a detailed look into the literature to see if, also in all the details, this is still the best choice. So, in summary, the material selection does not just depend on the required property profile, but also on the component shape and the production process. It's a complex process. This presentation focuses on the material selection strategy. So without the selection of the production method, just the material selection strategy. So if we start with all materials that are available to us here at the top, which is around 150,000 different engineering materials, we first have to translate the design requirements and express them as a function, constraints, objectives, and free variables. Now, what I exactly mean by that will become clear in the example on the next slide. Then there is a screening step, and in this screening step we use the constraints to eliminate materials that cannot do the job. The next step is to rank the materials using the objective. So we'll find materials that can do the job best, and the best material is then ranked as number 1. And then the last step is to seek documentation. So it's always good to look at the details and research the family history of the top ranked candidates, just to be sure that in terms of all the details that are there, you're making the right final choice. Now let's look at an example of the translation step, and we do that for heat sinks for microchips. So what you see here in this picture are the microchips, and they're connected to a heat sink to make sure that the chips are not overheated. So all the heat that is being generated by the chips has to be conducted away from the chip through these heat sinks, and they have here cooling fins so all the heat can be carried away. Now there are some design limiting properties. There's a maximum surface temperature, the electrical resistivity of this material for the heatsink, that has to be very high because we don't want to have any electronic interaction with the chip. And of course, if we want to conduct the heat away, the thermal conductivity of the material should be very high as well. So in the previous slide I said we have to make the translation step in terms of the function, constraints, objective and free variables. So the function here is a heatsink. We're talking about a heatsink, or as I wrote down here in Dutch, warmteafvoer. Now then we have the constraints, which we will later on use for the screening. And the constraints are that the material must be a good electrical insulator, and we don't want to have any interaction, electronic interaction with the chips. And the maximum operating temperature should be something like 200 degrees. And the material should still function up to those temperatures. And there might also be some geometric constraints, and in this case all the dimensions for this heatsink, they have been specified. So we call those the geometric constraints, and up here the functional constraints. Now then we move on to the objective, and the objective is to maximize the thermal conductivity. Now what's the free variable? Well, in this case we only have one free variable, and that's the choice of the material. But sometimes, and in another example I will show you that, there are also a geometrical parameters that can still be a free variable, meaning we can still choose it. But in this case, the only free variable is the choice of the material, and that's of course what we're after. What is the best material for this application? At this stage, it's good to look at the difference between constraints and objectives. So what is a constraint? A constraint is an essential condition that must be met, usually expressed as a limit on a material or process attribute, and we use it for the screening. What's the objective? The objective is a quantity for which an extreme value is sought, and we use it for the ranking. So the table below here shows you some common constraints. That means we need to meet a target value of, for example, stiffness, strength, fracture toughness, thermal conductivity, electrical resistivity, magnetic remanence, optical transparency, cost, and mass. Examples of common objectives are, well, typically we want to minimize the cost, the mass, the volume, impact on the environment, or heat loss. Sometimes we want to maximize energy storage or heat flow, are examples of that. Let's return to our example of the heatsink for a microchip. In this slide I would like to illustrate to you how the screening and ranking can be done with the help of these Ashby graphs. Now what you see here in the Ashby graph is on the y-axis the thermal conductivity and on the x-axis the electrical resistivity. Now as a screening step we said that the material needs to have a high electrical resistivity, which is here represented by the symbol ρe. And suppose we've quantified what high is, namely it should be larger than 10 to the power 20 microohm times centimeter. So that means that all the materials that lie here on the right side, the right hand side of this graph, they fulfill the screening step. They pass the first screening step. So that's the screening, and then we'll have a look at the ranking. And we said we would like to find materials with the highest thermal conductivity. So that's here represented by the symbol lambda, and this expression tells us the material index M is lambda, the thermal conductivity. So what do we want to maximize? We want to maximize the material index M, meaning we want to maximize the thermal conductivity. Now I've placed this line arbitrary horizontally at some location in this graph, but we want to maximize lambda, so basically we want to move this line up, and when we move it up we find that aluminum nitride is in fact the material with the highest thermal conductivity, and that also satisfies our screening step, namely it's a material with a higher electrical resistivity than 10 to the power 20 microohm times centimeter. Now this graph, this bubble shows you that there is some spread in the different grades of aluminum nitride, but there are some grades of the aluminum nitride that have a high enough electrical resistivity to pass our screening step. So this is a way in which we use both a screening step and a ranking step to find the best material for this application, namely the aluminum nitride. You may wonder, out of curiosity, how does aluminum nitride conduct the heat but not the electricity? Well, maybe it's good to zoom in a little bit more into the material and explain you about the phonons. So suppose these little spheres are the atoms that build up the material, and when the material heats up, the atoms start to oscillate, to vibrate, and due to the oscillation of the atoms you can have elastic waves in the material. You can imagine that the atoms are connected by some imaginary springs, and due to this bonding between the atoms you will have elastic waves that appear as a result of the heat that is being introduced into the material. So these elastic waves, they can travel through the material, and that's basically what you see here, this part of the picture. If this is a piece of material which is hot on one side and which is cold on the other side, we find these elastic waves, these phonons, here with a high amplitude where the material is hot, and with a low amplitude where the material is cold. And these phonons have some mean free path over which they can travel through the material, and by traveling through the material they basically conduct the heat. So the heat is conducted through the material via these elastic waves, which we'll also call phonons, or in Dutch phononen. We now know how the aluminum nitride conducts the heat, but now look into the question, why does it not conduct the electricity? Well, for that we first look into the mechanism by which electrons move through the material and thereby conduct the electricity. Well, let's have a look at a single atom with the nucleus, and here the electrons circulating around it, and below here you see the energy levels of the atom. So here's the 1s orbital occupying 2 electrons, here's the 2s orbital, and there are also 2 electrons in it. The 2p orbital, 1, 2, 3, 2p orbitals, with each of them having 2 electrons, and here's the 3s orbital. Now this is the situation for a single atom, where we have these distinct energy levels for the electrons. And now we move on to an ensemble of atoms, and then the energy levels as you see them here for a single atom are split up. So this is the example where you have 5 atoms in close proximity of each other, and you see that the 3s energy levels are split up in 5 levels that are very close to each other, and the same happens for the 3p energy level. And you can imagine that if you have many of these atoms close to each other, like you have in a real material, there are even more energy levels than you can see here, those 5. You more end up in this situation where all the energy levels are so close to each other that in fact they're all overlapping, and you have a 3s band, and you have a 3p band, and even the 3p and the 3s bands in this case overlap. So if you want to have electrical conductivity, the electrons have to move from this occupied band, occupied with electrons, to this free band, and here the electrons can freely move once they're in this band throughout the material. So this is the way the electricity or the electrons are conducted through the material. So now that we know the concept of the energy bands, we have the conduction band and we have the valence band, so where the electrons are actually located in the material. We can now distinguish between the electronic structure of the metals, the semiconductors, and the insulators. So in the case of metals, we have the valence band and the conduction band overlapping, so electrons that are in the occupied band, they can, with a little bit of energy be promoted to the conduction band, and there is free conduction of and movement of the electrons. Now in the semiconductors, as you can see here, there's an energy gap or a band gap, and there's more energy required to promote an electron from the valence band to the conduction band. And the difference between the semiconductors and the insulators is that the energy gap is larger. So in fact it becomes impossible, or maybe I should say hardly possible, for the electrons that are located in the valence band to acquire enough energy to actually be promoted to the conduction band. So in the case of aluminum nitride, the band gap, or the energy gap that is here located, is 6.3 electron volt, and that is too high for the electrons to be promoted from the valence band into the conduction band. In other words, this is an insulator. So this is why aluminum nitride does not conduct the electricity, but it does conduct the heat via the phonons. I will now give a recapitulation of the basic electrical properties of materials. If you're already familiar with these electrical properties of materials, then you can skip the next 10 slides. We will use what is explained in the next 10 slides in the rest of the presentation, so it's some basic background knowledge. Some basic terminology. Electrical conduction refers to the transport of charge. Electrical insulation refers to the prevention of charge flow. Dielectric behavior refers to behavior in an electric field without conduction. And what happens in a dielectric material is that you will have a small charge displacement as a result of an electric field that you apply over the dielectric material. So that's, for example, relevant for a capacitor, or in Dutch a condensator. So in this way you can temporarily store charge or electrical energy in an electric field that polarizes an insulator. Materials for electrical devices. So which materials do we have for electrical devices? What categories do exist? So we have the conductors, the semiconductors, and the insulators. And when we look at the conductors, well, we can find underneath that the superconductors, which have zero electrical resistivity. So electricity is conducted without any losses. And we have the semiconductors. There are the intrinsic semiconductors, the pure silicon and germanium. And we have the extrinsic semiconductors, and those are doped silicon or doped germanium. For the insulators, we can find piezoelectrics, pyroelectrics, and ferroelectric materials. Dielectric field. We give the electric field strength the symbol E, and it has units of volts per meters. So if we connect a battery to this material, there will be a potential difference over this material, here on the plus on the positive side, and here indicated by minus on the other side. So this potential difference over a distance x, here in meters, that gives you an electric field. So you see that here the potential difference divided by the distance over which the potential difference is applied, and there is a minus sign in front of the equation here because the electric field points from the positive towards the negative pole. The electric field will result in a force F on a charge, in this case a positive charge, and as a result the positive charge will move into the direction of the negative pole. there will also be a force on the negative charge as a result of the electric field, and as such the negative charge will move towards the positive pole. The current is indicated by the symbol I, and it's given in units of amps or amperes, and the amps are equal to coulomb per second, so the amount of charge moving per second. Then there is the current density indicated by J, and that's nothing else than the total amount of charge moving per unit area per second. So it has amps per square meter as units. So you can see that here in the formula as well. The current density is equal to the current divided by the surface area, the cross-sectional area through which the current is flowing. Now then it's important to note that if we have a battery here, from the negative side of the battery the electrons will flow through the lamp towards the positive side of the battery. But the conventional current, as we have a long time ago agreed upon, flows from the positive towards the negative pole. So the current flows from plus to minus, whereas we do know that the elementary particles, the elementary charge, is the electrons, and they will move from the negative electrode to the positive. Okay, this slide discusses the difference between the resistance and the resistivity. Suppose that we have a resistor with length L and a cross-sectional area A, and we apply a voltage difference V over the resistor. Then we can plot the potential difference, the voltage difference, against the current, and the slope of the curve that we then obtain is the resistance. R equals V divided by I, where I is the current. Now the resistance of the conductor is proportional to its length L, and it is inversely proportional to its cross-sectional area A. So in the form of a formula, the resistance R is proportional to the length divided by A, the cross-sectional area, and the proportionality factor is rho E, and that is a material property, and it's called the resistivity. And the units of the resistivity are ohms times meters, and in Dutch we call that the soortelijke weerstand of resistiviteit. This slide discusses the conductivity. The electric field makes charge carriers move, causing a current to flow. The resultant current density J is proportional to the electric field E. You can see that here in the equation. So this is the current density, and it's proportional to the electric field E, and the proportionality constant is kappa E, and that's the electric conductivity. And of course the conductivity is related to the resistivity, and that's related via this formula. So the electric resistivity is 1 over the conductivity. So the units of the conductivity are 1 over the units of the electric resistivity, so it's per ohm per meter. So the equation that we previously found, you can see it here. That's the current density, which we found to be equal to the electric field multiplied by the conductivity, and we can write that of course also as E divided by the resistivity rho, and we can rearrange this equation and write it in this form, because the current density is equal to the current I divided by the cross-sectional area. The 1 over rho term, we already have it from this equation, and the electric field we can write down as the potential difference divided by the length over which the potential difference is applied. And then we can rearrange this equation in such a way that the potential difference is I times this term rho times L divided by A. And we had previously already found that this term here is nothing else than the resistance, so we can also write this as R, and then we find V equals I times R, which is nothing else than Ohm's law, as we already knew. The dissipated power P in watts or joule per second is a result of the resistance, and in Dutch we call it the gedissipeerde vermogen. And the dissipated power P equals I times V, and with the help of Ohm's law we can also write that as I squared times R. In this section we're going to discuss how to derive a material index in case the conductivity of the material is an important criterion in the selection of the material. The material index is used for ranking the materials. So you can use the material index to rank all the materials that fulfill the screening stage, and of course the best material is ranked the highest. So the property or property group that maximizes performance, or in Dutch prestatie, for a given design is called its material index. So what is the difference between property or property group? You can have one property, namely the conductivity of the material, or you can have a combination of properties, for example conductivity and yield strength. Then we have a property group, and they can all be incorporated in a material index. Now an example of an Ashby graph in which several material indices M are displayed are given here in this figure. This is not related to any electrical properties, but this is related to mechanical properties. Here you see the Young's modulus of the material in gigapascal versus the density rho in megagrams per cubic meter. And the important point to make here, what you see is that you can have different material indices. In this case here you see the elastic modulus or Young's modulus to the power 1 over 3 divided by rho. Here you see the square root of E divided by rho, and here you see E divided by rho. In other words, you have three different material indices derived for three different conditions that we will not go into now, but it leads to three different graphical representations of the material index. So you see three lines in this graph representing the three material indices, and depending on the situation, whether you have derived it for this situation or whether you have derived the material index for that situation or that one, you see that the slope is different, meaning if you want to find the best material, you will find for the three different cases three different optimal materials, because you're shifting this line for example upwards to find the highest value for the material index, and in this case for this line it would end up here somewhere as the best material to be found within the family of ceramics, whereas in this case the composites might also be a very good option to choose from, or if you look at this case it's more in the direction of the foams where you will find the material with the best performance. This slide shows you the steps that you have to take to derive a material index in the case that you have a free geometrical parameter. From the example it will become clear what exactly is the geometrical parameter that is still free, but the 5 steps that we will go through are firstly the objective function, or in Dutch de doelfunctie. Then we will find an expression for the boundary condition. de randvoorwaarden in Dutch. Then we will find an expression for the free parameter, de vrije parameter, and then we'll substitute the free parameter in the objective function. So what we find here, we'll insert it into the objective function, and in the last step we can then extract a material index. The derivation of a material index is best illustrated via an example. In this example, we want to select a material for the cheapest electrically conducting cable with a given length L. The boundary condition in this case is that the electrical resistance of the cable should be lower than R max. And this can be a quantitative value, which we now call just R max. The free variable in this case is the cross-sectional area A of the cable that can still be freely chosen. So the question now is, derive a material index that needs to be maximized, because we always maximize the material index, in order to select a material that results in the cheapest cable and that has an electrical resistance that is lower than R max. So we will go through the steps that we just discussed, and the first step was the objective function. So what is the objective? The objective is to minimize the cost, and we call that C in euros, of the cable. And we have to derive or make an objective function, or in Dutch a doelfunctie, and we can write the doelfunctie or the objective function in this way. The cost of the cable is called C, and that's equal to the cost of the material of the cable in euros per kilogram. And if we have this volume of material of the cable, namely the cross-sectional area A times the length of the cable, we have to multiply it by rho, the density of the material, to obtain here, when you multiply it with the cost per kilogram, to obtain here the total material cost of that volume of cable. Now the second step is to find an expression for the boundary condition. And what is the boundary condition? Well, the boundary condition is that the resistance should be smaller than a maximum value for the resistance R max. So the equation that we can write down for the boundary condition is simply by rewriting this resistance as we had before in terms of a material parameter, and because we're deriving a material index, and that's the resistivity rho E, and then we have to multiply that by L divided by A, and this term together is our resistance, and this expression should of course still be smaller than the specified maximum resistance. So this is our equation for the boundary condition. The third step is to find an expression for the free parameter. So what's the free parameter? The free parameter is A, the cross-sectional area, and if we want to find an expression for the cross-sectional area, we just have a look at the previous expression from the boundary condition, and we simply rewrite the previous expression where we find an explicit equation for the cross-sectional area A, which in this case equals the resistivity times L divided by R max. The fourth step was to substitute the expression for the free parameter into the objective function. So let's repeat what is the objective function. We previously found that the cost equals A times L times rho times Cm, the cost per unit of weight of the material, and the free parameter we had found an expression here for the cross-sectional area A. So what we do now is simply substitute equation 3 into equation 1, and if we do that we get this expression for the total cost of the cable, there is a geometrical parameter L. There's one related from the boundary condition to the resistivity, to the resistance, and then there are three material properties: the resistivity, the density, and the material cost per kilogram. So in the last step we're going to derive the material index, or isolate the material index from the equation that we obtained from the previous slide written down here. You can see that the cost is proportional to three material parameters and a material index. Well, you're only interested in the material parameters. So if the cost needs to go down, if that is our objective, then the three material parameters that we can play with are the ones that are written down here, and they have to go down as well. If rho E, rho and Cm go down, if that product goes down, then the cost of the cable will also go down. Now the fact is that material index, we always define it as something that you want to maximize. It's just an agreement that we made. So the material index always needs to be maximized. So in this case we want to minimize the cost, but we want to have a material index that needs to be maximized. So very simple, 1 over the cost leads to an expression that you have to maximize. So the material index in this case is 1 over the expression that you find here, rho E, the resistivity, times rho, the density, times Cm, the cost per kilogram of the material. So remember, the material index only contains material parameters. So we now have found our material index related to this problem, and we would like to apply this material index to an HP plot, because then we can find which is the highest ranked material with the highest performance related to this problem. So we need to do one more step, and before we go to the Ashby plot, and that's basically we're going to manipulate this equation, the expression for the material index that we have found, and we do that manipulation because that is below here, because in the Ashby plot you typically have the logarithmic value of a material property, for example the resistivity, against another material property, and in this case we will look at the product rho times Cm. So we would like to rewrite this expression, and we do that in the following way. If you take the logarithm of both sides of the equation, we have on one side the logarithm of m, and on the other hand we have the logarithm of 1 over rho E times rho times Cm. Of course we can rewrite this in the following way, minus log rho E times rho times Cm, and of course we can rewrite this in this way. Now, in a plot where, an Ashby plot, where you put the logarithm of rho E on the y-axis, and where you put the logarithm of rho times Cm on the x-axis, you get a linear expression, just like this one, y equals a times x plus b, where a is the slope of the linear curve, and b is where it intersects with the y-axis. So after rewriting this expression, we find that the slope of this straight line has a value of -1, and this minus here indicates that we have to move the line to the lower left corner to maximize the material index. Now that will become clear in the next slide. So now we move on to an Ashby plot, and let's first have a look what is plotted on the y-axis. So here we see the electrical resistivity, rho E, and it's expressed in units of micro-ohm times centimeters, and you can see indeed that we plot things on a logarithmic scale, and in this case it's a special logarithmic scale because from one unit we go from 10 to the 9th to 10 to the power 12, so it's a step of 3 orders of magnitude. On the x-axis we plot the density times the price, so this is the material density times the price per kilogram, so in fact combining the two gives you the price per cubic meter. Alright, all the material properties have been displayed in this graph. Yeah, so for all the materials that is in the SES EduPack database, you see here what its value is for the electrical resistivity and what its value is for the density times the price. Now the different colors in the plot refer to the different material families, so the red, for example, is the family of metals. Now we have derived this beautiful material index, and in the previous slide we have also rewritten this material index by taking the logarithms from both sides of this equation, and the graphical representation of this material index is basically given by this line, and here you see the slope -1 that we found in the previous slide. Now once we have this line, it basically means that all the materials that lie on this line have the same performance because they have the same material index, so they perform equally well. And because we noticed in the previous slide that we have to move this line to the lower left corner if we want to increase the material index. So specifically, that's specific for this equation. After we have rewritten this equation in terms of the logarithm of m, like we have done on the previous slide, we find that we have to move this line in this direction to maximize the material index. So if we do so, we will find that aluminum is in fact the best choice for this problem. So aluminum has the lowest cost while still fulfilling our boundary condition that the resistance of the cable should be below our R max. So that's a nice and maybe slightly counterintuitive outcome of this analysis. Maybe you thought copper would be the best choice, which of course has a very low resistance, this material, but it's relatively expensive compared to aluminum. So that's why aluminum is the best choice. Yeah, and a point of attention now. So we found that aluminum is actually a better / cheaper choice than copper for this problem. And in fact, aluminum can safely replace copper in electrical equipment in case proper precautions are taken, because otherwise there is a risk of a higher risk of fire. So here you see a device which obviously was set on fire by accident, and yeah, you also see that different wires, copper wires have been used and aluminum wires have been used in this device. So what's the problem? Well, the problem is that, or that may arise, is at aluminum copper connections, because you have a difference in thermal expansion. So due to the current that flows through the material, it will slightly heat up, and if there is a difference in thermal expansion, upon heating, one material will expand more than the other. At the same time, at higher temperatures, some creep may take place in the aluminum. That basically means that the aluminum is also deforming, changing its length due to the elevated temperature if there is some tension on it. So what can happen due to these two different factors? The connection can loosen a bit. If that happens, then you get an increased resistance. That means the heat locally will increase. That will induce oxidation of the aluminum, more oxidation of the aluminum, because the aluminum oxide is a bad electrical conductor, you will have an increased resistance, and that will lead to more creation of heat, etc. And before you know it, you have a fire. So, in summary, what to do for material selection in case you have a free geometrical parameter. Well, after the screening step, you determine the material index for the ranking. And you do that according to the following 5 steps. First, you derive or define an objective function, doelfunctie in Dutch. Then you find an expression for the boundary condition, de randvoorwaarde. Third point is find an expression for the free parameter, voor de vrije variabele of de vrije parameter. The fourth point is to substitute the free parameter in the objective function. And last, extract the material index. Now, once you have the material index, you can plot the material index on an Ashby graph by determining the slope and move the line in the direction of increasing m, and then you will find the best material for this particular problem that you're looking into. Now let's return to the beginning of the lecture, where we looked at a case where there was no free geometrical parameter, and we still managed to have a material index. So how did we do that then? Well, we were looking at a material for this heatsink, so that the microchips could quite easily get rid of their heat via this heatsink. And we first said we do a screening step. We only take into consideration materials with a resistivity that is higher than 10 to the power 20 micro-ohm times centimeter. And then we did the ranking based on the material index, and since we did not have a free geometrical parameter, the problem was very easy, and we want to find the material with the highest thermal conductivity, which is here in this case symbolized by lambda. So by basically moving this green line up, we found aluminum nitride here to be the best material for this particular problem. In this section I will explain to you what a dielectric material is and what properties it has, and we will derive a material index for the maximum amount of energy that you can store per unit volume in a dielectric material, which is convenient if you want to make very small capacitors. So the main goal of this part of the lecture is the selection of a dielectric material with the highest energy density in order to store as much energy per unit volume in a capacitor, which is interesting for miniaturization. For example, in the iPhone 6 are 730 capacitors, and everything of course has to be as small as possible. So the challenge here is to find an appropriate material index for ranking the materials that can serve as a dielectric material for a capacitor. In order to understand dielectric materials, we first need to understand the concept of the electric dipole moment. So first look at an induced atomic dipole. That is dipole formation of an individual atom as a result of an applied electric field E, and that leads to displaced charge. So, in figures, suppose we have an atom, and the atom has a nucleus, and around it there is the electron cloud. Now this is how the atom looks like when there is no electric field applied. Now we do apply an electric field, and what happens is there is displacement of charge under the influence of the electric field. So here is now the atomic nucleus located, and the electron cloud is now shaped like this in the presence of this electric field E. Now this situation we can schematically also represent by the displacement of charge, the plus charge on this side and the minus charge on that side, and they are separated over a distance given by this bar. Now then we move on to this picture, and we represent it now in this way. There is a negative charge Q, and there is a positive charge Q, and they're separated over a distance delta x. Then the dipole moment D equals the charge times the separation distance. And since the charge is coulomb and the distance is expressed in meters, the dipole moment will have as units coulomb times meters. Now this is what happens in case an atom experiences an applied electric field, but you can also have molecules like HCl that have a permanent dipole. And that's because the molecule itself is polar, which means that in this case the chlorine atom here attracts the electron a little bit more than the hydrogen atom here, which means that on average the charge is more negative here on the chlorine side, so that's indicated by this minus sign, and on the side of this hydrogen atom it's more positive. So you have a permanent dipole in this polar molecule, and that can be expressed by the same symbol as we used here before for the dipole moment. Moving on, we go to the electric polarization. So what is that? Well, that's basically the alignment of the dipole with the externally applied electric field E. So if we have our dipole again with the positive charge Q, the negative charge minus Q, as a result of the electric field E, a force will be applied on the charge, and it's in different directions depending on the sign of the charge. And in effect what happens is that the dipole moment will align with the electric field in this way. So the dipole moment here will move into this configuration. So then we can define the polarization, the electric polarization, as the sum of all the dipole moments divided by the volume. And if we again look at the units, the dipole moment had a unit of coulomb times meters, and the volume is of course in cubic meters, so that means that the polarization should be in coulomb per square meter. What is a dielektrische materiaal, or in Dutch a dielektrische materiaal? Well, it's an electrically insulating, it is non-metallic material that exhibits or can be made to exhibit an electric dipole structure. That is, there is a separation of positive and negative electrically charged entities on a molecular or atomic level. So we see here two plates, and in between this plate there is a dielektrische material, and you apply a voltage over these plates, and then there is an electric field that is being generated, and as a result of that there is also polarization of the electric dipole moments. So let's compare the situation of vacuum versus a dielectric material in between the plates, the metallic plates over which we apply potential difference. So suppose this plate is connected to the positive side of the battery, then the amount of charge on this plate Q is proportional to the electric field times the permittivity of the vacuum. So in the case of vacuum, we have here this electric field V divided by L, and where this is L, the distance between the plates. Now what if we put a dielectric material in between these plates? Well, what we will find is that much more charge can be stored in these plates in the presence of a dielectric material compared to the vacuum. And that is related to this polarization factor. So the amount of charge is again proportional to the electric field, where the permittivity of the vacuum is the polarization factor that we found before in the case of the vacuum. But now there is a polarization added to this equation, which leads to a larger amount of charge that can be stored on these plates if a dielectric material is present in between the plates. Now let's have a look at capacitors, or condensatoren in Dutch. But basically this is the same picture as in the previous slide, but now different representation. So if we consider a capacitor with a gap in between the plates, we have potential difference over these plates. Here's the plus side, here's the minus side. So the electric field runs from plus to minus, symbolized by the letter E. There's a distance T between the plates, and sometimes I used the symbol L in the previous picture. Sorry for that. But the potential difference here is indicated by the voltage V. The electric field is the voltage divided by the distance T. The charge on the plates is Q, and we use a small letter Q to indicate the charge density, which is Q divided by A, where A is then of course the surface area of the plates. Now let's have a look at capacitors and vacuum. So we're considering the situation where we have two plates, and in between these plates there's a vacuum, and if we plot the charge on these plates, the charge Q, against the potential difference, we measure this curve, and so-called capacity is the slope of this curve, so the charge per unit of voltage. And of course, if the potential difference becomes too high, you will have electric breakdown. Now, the charge density is proportional to the electric field, so we've seen this equation before. Q, the charge density, is proportional to the electric field, and epsilon E is the proportionality factor, which is the permittivity of a vacuum, and that has a value of 8.85 times 10 to the minus 12 farad per meter. Now this equation we can also rewrite in this form. So the charge density is the charge divided by the surface area, and the electric field is of course V divided by T, and we remain our epsilon 0. And we can rewrite that equation in this way. And if we now define this part as C, where C is the capacitance, or the dielektrische capaciteit in Dutch. So that basically is the amount of charge that can be stored per unit voltage difference. So C equals the permittivity of the vacuum times A divided by T. And the units of capacitance are in farad, and that per definition is coulomb per unit voltage, because it's a charge that can be stored per unit voltage difference. And this permittivity of the vacuum, you could see it as something like the capability of the vacuum to permit electric field lines. So we're now going to look into the situation where a dielectric material is placed in between the plates, and we apply a voltage difference again over these plates, and we measure the same kind of curve when we plot the charge against the potential difference. We have a curve like this where the slope is the capacity Q equals Q divided by the voltage difference. So the charge density is again proportional to the electric field, but the proportionality factor now is epsilon instead of epsilon 0, and epsilon in this case is the permittivity of the dielectric material instead of the vacuum. Now we define a relative permittivity, which is also called the dielectric constant, and we define it in this way. The capacity when the dielectric is in place divided by the capacity when there's no dielectric. So that's basically the permittivity of the dielectric material divided by the permittivity of the vacuum. So that's the relative permittivity. And relative because you divide epsilon by epsilon naught. And this relative permittivity is known as the dielectric constant of the material. So in this expression we can rewrite this expression in this way with the help of this formula. Now remembering that we had Q equals to C times V, and in this case the C is now written with epsilon, the permittivity of the dielectric material, and if we rewrite that with the help of this equation, we find that the capacity equals the permittivity of the vacuum times the dielectric constant times A, the surface area of the plate, divided by T, the distance that the plates are separated. So now we have a small intermezzo. We've seen that the charge density on a plate is proportional to the electric field and the permittivity of the vacuum, and we've seen that in the case of the presence of a dielectric material in between these plates, there's an additional polarization factor and more charge can be stored on the plates in the presence of a dielectric material. So we have this equation, and it's maybe good to see other forms in which we can write that, because the polarization, that's proportional to the electric field, and the proportionality factor is what is called the electrical susceptibility. So that is basically a measure how susceptible is the material to the polarization in an electric field. So if we can combine this formula with this one, we can write it in this way, and this formula we can also write in this way, where epsilon is the permittivity of the dielectric material, and that can be written as permittivity of the vacuum times the relative permittivity. So we also have this equation, and if we compare these equations now, we see that this relative permittivity is the same as 1 plus the susceptibility. So it's good to see and note how the different quantities are related to each other. Now let's have a look at some numerical values for the relative permittivity of different kinds of materials, which is also the dielectric constant. So for air, it's close to the one for vacuum, it's about 1, for polyethylene around 2, glass around 4, paper also around 4, water 88, which is of course because it has some it's a polar molecule. There's some charge distribution over the molecule, where the oxygen is a little bit more negative and the hydrogen is a little bit more positive. Titanium oxide 125, strontium, titanium oxide 300, lead, zirconium, titanium oxide around 3000. So a high dielectric constant allows a high amount of charge to be stored on plates. But there is a maximum related to the electric field, and that is related to breakdown. Yeah, what happens at dielectric breakdown? If an electric field is very large, typically of the order of 10 megavolt per meter, an electron can be detached from its parent atom and accelerated in the electric field. This can cause a cascade or dielectric breakdown, and that's what you see in both pictures in real life and here a schematic. Yeah, this is another very familiar example of dielectric breakdown, a thunderstorm. So at dielectric breakdown, the charge density is given by this equation, and that's something we basically have seen before this equation, except now for the electric field we fill in the electric field at breakdown. Now the electrical energy stored in the capacitor is given by this equation, half times Q, the charge, times the voltage, and if you remember we can also write Q as C times V, so that gives us an equation in the form of a half C times V squared. And the factor of half arises because half of the energy supplied by the battery for the charging of the capacitor
That's cool. Two.
In action.
Damn! That sucker's got yes, baby! Yeah, ready?
Oh, that one was good.
That was pretty good.
That was beautiful, man. Beautiful. Look at that.
capacitor is dissipated as heat in the resistor. Now this is maybe a nice movie to show you what happens. Now what's the energy density of a capacitor? So the energy density, if we call it U max, the energy per unit volume, it's simply the energy of the capacitor divided by its volume, and we can also write that as half CV squared divided by the volume here, the A, the surface area, and the thickness T. And we can also, with the equations previously shown, write it like this and then subsequently like that. So here we filled in the electric field at electric breakdown, and we made use here of the capacitance and how you can write that in these terms. So what is important in the end is the energy density U max is equal to half epsilon naught epsilon r times EB squared, and these two are in fact the material parameters. So our material index, finally we arrive at the material index, looks like this. It only contains the material parameters, and we want to maximize the energy density, and we also want to maximize the material index, so we can simply take from this formula only the material parameters and put it into the material index. So now we move on to an Ashby graph, and we plot on the y-axis the dielectric constant, or the relative permittivity, and on the x-axis we plot the dielectric strength, so the electric field at breakdown. And we can plot now our material index M in this graph, because as you can see, epsilon r is here on the y-axis and EB is here on the x-axis, and by rearranging this equation and taking the logarithm on both sides, we will find that the graphical representation of this material index is in fact given by this line, and this line has a slope of -2 on a double logarithmic scale, a double logarithmic graph. And you can see that these lines have or represent the maximum energy density, and in this case it's the line that corresponds to 1 kilojoule per cubic meter, here for 2, 5, 10 and 20 kilojoule per cubic meter. So as you move this line more to the upper right corner, the energy density increases, and what you can see is that a material like nylon has a relatively high energy density. So why is that? Well, here you see a schematic representation of the nylon 6 molecule, and you see also that it has polar parts. So there is a permanent charge displacement present in this molecule. Now maybe it's good to have one more look at our material index and what we arrive at when we take the logarithm on both sides of this equation. So on one side we have the logarithm of the material index, and then we have the logarithm of the dielectric constant, and we have 2 times the logarithm of the electric field at breakdown. So if we rearrange this equation in such a way that on this side we have the logarithm of the dielectric constant, that's what we have plotted on the y-axis of our Ashby graph, and then we see here that the slope of the line, here represented by this A, should be -2, and the x-axis was we had the logarithm of the electric field at breakdown, and we see here a plus sign for in front of this term, and that basically means that we have to move the line to the top right corner, and that was exactly what we had done in the previous slide. So once more, we see here the dielectric constant and the dielectric strength. It's a similar graph as 2 slides ago. So the lines here with the slope -2, they again represent the energy density. So the amount of energy that you can store in a dielectric material per unit volume. Now this graph is somewhat extended, and you see here now also energy densities, ranging up to 1,000 or 10,000 kilojoule per cubic meter, and you see that there are materials like barium titanate that have really high energy densities, and that's to a large extent due to the fact that this material has a very large dielectric constant. Now there are also capacitors made out of tantalum pentaoxide, and they have dielectric constants of 27, lower than the ones for the barium titanate, but they have electric fields that break down that are much higher, beyond the scale here. So they have roughly around 5,000 kilojoule per cubic meter of maximum energy that can be stored. So how to make the tantalum capacitor? Well, you have a tantalum wire, which functions as the anode, and you have tantalum particles that you sinter together, and you let, in green here, grow an oxide layer on top of it, so nanometer thin oxide layer that acts as the dielectric material. And then you also need a cathode, in this case of manganese dioxide, and yeah, this gives you a high surface area for this capacitor. Now the tantalum capacitor is, for example, of interest for miniaturization. So if you can store a high density, you can make capacitors smaller. Regarding tantalum, there is one problem. It's considered to be one of the critical raw materials for the EU, and that basically means that the European Union considers tantalum to be a material which is very important for the economy, but at the same time there's a risk of the supply of tantalum because it's only produced in a few countries in the world. But that's a completely different subject, also very interesting, but for a different presentation.
In this video, we're going to commit random acts of destruction and learn a few things about capacitors along the way. Ultracapacitors are like regular capacitors, except they can hold much more energy. Here's an example. This is a 560 microfarad 200 volt electrolytic capacitor, and it's about as big as you'll ever see on a consumer circuit board. The energy stored in a capacitor is given by this formula. If I apply it to this capacitor, I can see that it can store a maximum of 11.2 joules. In certain circumstances, that's enough to do some serious damage. Now, the ultracapacitors I bought are 2,600 farads, and that's not a mistake, 2,600 farads, with a maximum of 2.5 volts. That means that one of these ultracapacitors can store 8.1 kilojoules of energy, which is a ridiculous difference. So let's see what a few kilojoules can do. Here I have the ultracap charged to 2.35 volts, and you can already see this thing means business. Let's start out by burning some soldering braid. Now let's melt an inductor. Here I'm shorting the cap across a 5-cent coin. Whoa. Wow, that beaver really took a pounding. And I thought it was fun to make these PCB traces light up like glow wire. Finally, let's make some random sparks again, just for the hell of it. And you know what's crazy? After all that, the cap is still charged to 1.7 volts. If you apply the capacitor energy storage equation before and after blowing things up, you can see that I used up 3.4 kilojoules of energy. So there's a lot left over.
Yeah, and then we have the supercapacitors.
In this video, we're going to commit random...
So let's have a look at these special barium titanium oxide materials, which have such high dielectric constants. So it's a ferroelectric material, and that means that it has a spontaneous polarization below a certain temperature, which is called the Curie temperature. And here you have the crystal structure, and what you can see is that there are barium 2+ ions located at the corners, and there are oxygen 3- atoms or ions placed at these locations, and there's a titanium 4+ ion here in the middle. And in this case, the titanium atom is slightly displaced upward, and in this case it's slightly displaced downward, and that means that the polarization can easily switch from up to, as you can see here, down. So what you get is ferroelectric domains. They're like the magnetic domains. So you get these domains that you see here, and in such a domain the polarization is all in the same direction, and this microscopic structure of the material is what you would see in the case that there is no applied electric field. And then you have a closed circuit, and you have these with these 4 domains, and within one domain the dipoles are all in the same direction. And what you see here is what is called the domain wall. Now when you do apply an electric field, then you see that all the dipoles are aligned in the same direction, so you get polarization in one direction. So this material here is polarized, and here there is no net polarization. Locally within a domain there is polarization, but net there is no polarization in this material. So what happens when you apply an electric field? The polarization increases along this curve, and then you decrease the electric field, and then the polarization reduces, but you have still a remnant polarization. You have to reverse the electric field, and only then, when you increase it, the polarization again goes to 0, and this is what is called the coercive field, the electric coercive field. And then when you continue increasing the electric field in the other direction, the polarization also reverses its direction compared to what we have seen here. And again it reaches a saturation level, and if you then switch the electric field in the same way as in here, the polarization goes down, there's a remnant polarization, and you have to continue increasing the field until you really reduce the polarization to 0, and you here again have reached that point at the coercive field EC. Now let's start with some exercises. The first exercise is very simple. It's the same as what we've actually done before. The maximum energy density of a capacitor. We want to select the material with the highest energy density. Again, we can do that with the /EduPack software, and it's exactly the same as the exercise that we've seen before. The only thing that we change now is that on the y-axis we now plot the electric field at breakdown, and on the x-axis we put the relative permittivity, or the electric constant. So the material index is exactly the same. This was the graph that we have seen before, and now what we're going to do is switch the axis. So what's here will now be placed there, and vice versa. So we have the same plot except for the axes that are changed. Now if we then look with /EduPack, we see now on the y-axis EB, the electric field strength at breakdown, and we see the dielectric constant now on the x-axis. Now what has changed? If you take the logarithm of on both sides of this equation, and you do the whole exercise that we did before, we find a slope of -1/2. So instead of -2, it's -1/2. Again, we need to move the line to the top right corner, and you see that again, of course, we find nylon as the material with the highest energy density. And of course, in the previous graph, the dielectric constant run up to something like 10,000. So there are more materials in this region, like the barium, titanium oxide that we've discussed before. But here it's more about the principle. Okay, this second exercise is completely in Dutch. So I will read it in Dutch. Er moet een keuze gemaakt worden voor het materiaal van een draad die een elektrische stroom I kan geleiden. Het doel is om de kosten te minimaliseren. De totale kosten KT in euro, die zijn gerelateerd aan de draad met een gegeven lengte L in meters, zijn de optelsom van twee bijdragen. Ten eerste de materiaalkosten. Om de materiaalkosten te minimaliseren moet het oppervlak van de dwarsdoorsnede A van de draad zo klein mogelijk zijn. Ten tweede de energiekosten. Door energieverliezen tijdens het gebruik van de draad. Om het verlies van energie te minimaliseren, dat wordt gedissipeerd in de vorm van warmte tijdens het gebruik, gedurende een tijd t, van de draad, moet het oppervlak van de dwarsdoorsnede van de draad zo groot mogelijk zijn. Hierdoor zijn de elektrische weerstand, de resistance R, van de draad en het gedissipeerde vermogen P zo klein mogelijk. Neem aan dat de elektriciteitsprijs per joule gelijk is aan EP in euro per joule. Er is dus een optimaal oppervlak A-opt van de dwarsdoorsnede waarvoor de totale kosten minimaal zijn. Het optimale oppervlak hangt af van de keuze van het materiaal voor de draad. Met andere woorden, de totale kosten worden geminimaliseerd door de optimale combinatie te kiezen van het oppervlak A en het materiaal van de draad. De figuur hiernaast geeft ter illustratie KT, de totale kosten, als functie van het oppervlak A, weer voor 3 verschillende materialen voor een tijd die niet heel kort is en niet heel lang. Want in deze twee extreme situaties zouden de materiaalkosten of de elektriciteitskosten domineren respectievelijk. Dus op de y-as zien we hier de totale kosten, hier de dwarsdoorsnede van de draad en hier voor 3 materialen, materiaal 1, materiaal 2 en materiaal 3, hoe de kosten variëren met de dwarsdoorsnede van die draad. En je ziet dus dat je voor 3 verschillende materialen een minimum vindt, een ander minimum vindt en ook bij een andere dwarsdoorsnede. Nou, de hoofdvraag is, leidt een materiaalindex af die moet worden gemaximaliseerd om tot een materiaalkeuze te komen voor de draad, waarbij de totale kosten van de draad wordt geminimaliseerd en geeft die materiaalindex. En de deelvragen die daarbij horen zijn, geef de formule voor de doelfunctie en geef de formule voor de vrije parameter. Nou, de totale kosten van de draad zijn de optelsom van de materiaalkosten en de energiekosten tijdens het gebruik van de draad. Dus dat hebben we eventjes in formulevorm op deze manier weergegeven. Totale kosten is materiaalkosten plus energiekosten. Nou, die materiaalkosten kunnen we ook schrijven als de kosten van het materiaal per kilogram. En als we een bepaald volume van een draad hebben met een dwarsdoorsnede A, een lengte L, dan moeten we dat nog vermenigvuldigen met de dichtheid van het materiaal. En dan staan hier dus uiteindelijk de materiaalkosten. De energiekosten zijn het vermogen. Als je dat vermenigvuldigt met de tijd, dan hebben we hier de energie. En als EP de energiekosten zijn, het aantal euro per joule, staan hier dus de totale kosten voor de energie. Nou, het gedissipeerde vermogen P is gegeven door de formule die we al eerder gezien hadden, I kwadraat maal R. En die elektrische weerstand R hadden we eerder ook al gezien, die wordt gegeven door deze formule. De lengte van de draad, de dwarsdoorsnede, maal de soortelijke weerstand. Nou, als we dat allemaal bij elkaar hebben, dan kunnen we de totale kosten dus vinden door vergelijkingen 2 en 3 in 1 in te vullen. En dan krijgen we dus deze uitdrukking voor de totale kosten. Nou, we hadden al gezegd dat die parameter A, de dwarsdoorsnede van de draad, dat is de vrije parameter. En het optimale oppervlak wordt dan ook gevonden door de afgeleide te nemen van deze functie naar dat oppervlak A en die gelijk te stellen aan 0 en op te lossen voor A. En dan hebben we dat minimum gevonden wat we in die grafiek hiervoor zagen. Dus als we dat doen, vinden we deze uitdrukking voor dat optimale oppervlak. En daar zitten materiaalparameters in. De ρe, de ρ en de cm herken je hierin. Nou, als we dan het optimale oppervlak gevonden hebben, dan kunnen we dat weer substitueren in de uitdrukking voor de kosten. En de minimale totale kosten worden dan door deze formule uiteindelijk gegeven die je hier ziet. En die kan je herschrijven op deze manier. En als je dat zo stap voor stap volgt, vind je uiteindelijk een uitdrukking die hier is opgeschreven. En wat ik eigenlijk gedaan heb is, ik heb alle materiaalparameters bij elkaar gezet. En ik heb alle niet-materiaalparameters, zoals een geometrische factor, de lengte, heb ik in een andere term neergezet. Maar voor ons is dus dit cluster van materiaalparameters belangrijk. Nou, de materiaalparameters zitten allemaal rechts in die vergelijking 6 die we net gezien hadden. En de materiaalindex die moet worden gemaximaliseerd om de kosten te minimaliseren, is dus deze. Het enige verschil met de vergelijking van de vorige slide is dat we nou 1 gedeeld door die wortel uit ρe maal ρ maal cm hebben genomen. En dat heeft alles te maken met het feit dat een materiaalindex altijd gemaximaliseerd moet worden. Dat stond ook in de vraag. En wij willen de kosten minimaliseren, dus die twee zijn omgekeerd evenredig met elkaar. Dus een equivalente materiaalindex, omdat al deze materiaalparameters met elkaar vermenigvuldigd worden en daar de wortel uitgenomen wordt, kan je ook op deze manier schrijven. Het zal uiteindelijk leiden tot het vinden van hetzelfde optimale materiaal. Of je deze formule neemt of die, dat maakt uiteindelijk niet uit. Als deze parameters een andere macht hadden hier, dan kan je dit niet zo toepassen. Dus je moet er wel eventjes op letten dat al die parameters worden met elkaar vermenigvuldigd en je neemt daar ook allemaal de wortel uit. Dan mag je dat ook op deze manier opschrijven als je op zoek gaat naar het meest optimale materiaal. Nou, als we dan met behulp van 6 Edupak weer een Ashby-grafiek maken waarin alle materialen zijn geplot, dan kan je bijvoorbeeld op de y-as de elektrische soortelijke weerstand uitzetten. Op de x-as kan je de dichtheid maal de prijs uitzetten. Dus dat is eigenlijk uiteindelijk de prijs per eenheid volume wat hier staat. Nou, en als we deze formule, deze materiaalindex, als we daar aan beide kanten de logaritme van nemen en we gaan kijken wat dan de helling is, dan zie je dat hier een helling van -1 bij hoort. Dus de grafische weergave van deze materiaalindex is gegeven door deze lijn. En die kan je natuurlijk op en neer schuiven. En in dit geval moeten we hem naar linksonder verschuiven om de materiaalindex te maximaliseren. Dus wat vinden we dan uiteindelijk? Dan vinden we uiteindelijk dat aluminium de beste keuze is, de goedkoopste keuze is voor dit probleem.
Of destruction and learn a few things about capacitors along the way. Ultracapacitors are like regular capacitors, except they can hold much more energy. Here's an example. This is a 560 microfarad 200 volt electrolytic capacitor, and it's about as big as you'll ever see on a consumer circuit board. The energy stored in a capacitor is given by this formula. If I apply it to this capacitor, I can see that it can store a maximum of 11.2 joules. In certain circumstances, that's enough to do some serious damage. Now, the ultracapacitors I bought are 2,600 farads, and that's not a mistake, 2,600 farads, with a maximum of 2.5 volts. That means that one of these ultracapacitors can store 8.1 kilojoules of energy, which is a ridiculous difference. So let's see what a few kilojoules can do. Here I have the ultracap charged to 2.35 volts, and you can already see, this thing means business. Let's start out by burning some soldering braid. Now let's melt an inductor. Here I'm shorting the cap across a 5-cent coin. that beaver really took a pounding. And I thought it was fun to make these PCB traces light up like glow wire. Finally, let's make some random sparks again, just for the hell of it. And you know what's crazy? After all that, the cap is still charged to 1.7 volts. If you apply the capacitor energy storage equation before and after blowing things up, you can see that I used up 3.4 kilojoules of energy. So there's a lot left over.
At the moment of dielectric breakdown with a capacitor.
And action.